This is an assignment on use of ICT in education for online and blended learning. In this module, we will talk about AC series circuit. AC circuits. Rules and laws developed for DC circuits apply equally well for AC circuits. Analysis of AC circuits require vector algebra and use of complex numbers. In AC circuits, voltages and currents are expressed in phasor form, and they are expressed as RMS or effective values. Figure 3.1 gives an example of an AC circuit. Phasor diagram of resistor. In resistors, voltages and current of a resistor will be in phase. So impedance of a resistor is represented by ZR is equal to R angle 0 degree. R angle 0 degree is expressed in polar form. So for getting the value of current flowing through the resistor, we have simply divided voltage by the resistance, which gives us angle I angle theta. By observing the phase angles of voltage and current, we see that there is no phase difference between them. Hence, from figure 3.2, we can conclude that in a resistor, the voltage and current are in phase with each other. Phasor diagram of inductor. The current through an inductor lags the voltage by 90 degree. The inductive reactance is given by j omega L, where j is the complex number equal to root over minus 1. Omega is the angular frequency, which is equal to 2 pi f, where f is the frequency of the supply and L is the inductance. So inductive reactance is given by XL angle 90 degree. For getting the current I, we have simply divided voltage by the inductive reactance. So we have got the current I is equal to I angle theta minus 90 degree. As we can observe, the current is lagging 90 degree behind the voltage, as can be seen from figure 3.3. Phasor diagram of capacitor. Current through a capacitor leads the voltage by 90 degree. So Xc is equal to 1 by j omega c, and current through capacitor is equal to I angle theta plus 90 degree. We can observe from figure 3.4 that the capacitive current IC leads the voltage VC by 90 degree. Frequency effects on capacitive reactance. As in capacitive reactance, as seen from the previous slide, can be given by Xc is equal to 1 by omega c. So impedance of a capacitor decreases as the frequency increases. For frequency f equal to 0, omega will be 0, so the impedance of the capacitor will be infinite. And for a series RC circuit, total impedance approaches R as the frequency increases. Frequency effects on inductive reactance. Impedance of an inductor increases as frequency increases. At DC, that is f equal to 0 Hz, inductors look like a short. At high frequency, it looks like an open. Figure 3.6 gives variation of inductive reactance with the variation of frequency. AC series circuit. Impedance vectors will appear in either the first or the fourth quadrant because the resistance vector is always positive. When the impedance vector appears in the first quadrant, the circuit is inductive. If the impedance vector appears in the fourth quadrant, the circuit is capacitive. AC series circuit. Current everywhere in a series circuit is the same. Impedance used to collectively determine how resistance, capacitance and inductance impede current in a circuit. Z is equal to R plus Jx, where Z is the inductance, R is the resistance and X is the reactance. So reactance is nothing but the sum of inductive and capacitive reactance, which is given by XL minus XC, where XL is equal to j omega L and XC is equal to 1 by j omega C, where L and C are inductance and capacitance of the circuit elements. Total impedance in a circuit is found by adding all individual impedances vectorially. From the given figure, we have several different impedances connected in series, Z1, Z2, Z3 up to Zn. So the equivalent impedance is given by Z1 plus Z2 plus Z3 up to Zn. Voltage divider rule. Voltage divider rule works the same as the DC circuit. From Ohm's law, if two circuits are connected in series, then Ix is equal to It, where X and T circuits are connected in series. So Vx by Zx is equal to Vt by Zt from Ohm's law, and Vx is equal to Zx by Zt into Vt. Kirchhoff's law. KVL is same as in DC circuit. Kirchhoff's voltage law in AC circuit states that phasor sum of voltage drops and rises around a closed loop is equal to 0. From figure 3.7 we can see that the phasor sum of voltage across A, B and C is equal to 0. Kirchhoff's current law is same as in DC circuits. Kirchhoff's current law for AC circuit states that summation of current phasors entering and leaving a node is equal to 0. Current must be added vectorically. Currents entering are positive and currents leaving are negative. From figure 3.8 we can observe that the currents I1, I2 and I3 are moving towards the node, whereas current I4 and I5 are leaving the nodes. So current I1, I2 and I3 are treated as positive and current I4 and I5 are treated as negative. The sum of all these five currents are found to be 0. In a series RL circuit, impedance increases from R to a larger value. In a parallel RL circuit, impedance increases from a small value to R. Corner frequency. Corner frequency is a breakpoint on the frequency response graph. For a capacitive circuit, omega C is equal to 1 by RC is equal to 1 by tau. For an inductive circuit, omega C is equal to R by L is equal to 1 by tau. Series resonance. In a circuit with R, L and C component combined in series parallel combination, impedance may rise or fall across a range of frequencies. In a series branch, impedance of an inductor may equal the capacitor. Then in that case, impedance would cancel, leaving impedance of resistor as the only impedance. Such condition is referred to as resonance. From figure 3.9, we must discuss that resonance condition. Here XL gives the variation of inductive reactance with respect to frequency and XC gives the variation of capacitive reactance with respect to frequency. At 0 Hz, that is as frequency equal to 0, capacitive reactance was infinite as can be observed from the figure, and inductive reactance was 0, which can be observed from a figure as well. When the frequency is increased, capacitive reactance increases and capacitive reactance decreases and inductive reactance increases. So there comes a point at which both inductive reactance and capacitive reactance are equal, which is shown in the figure XL equal to XC. At this point, even though the resistance, inductance and capacitance are connected in series, the circuit will show the properties of only a resistance. At this point, XL is equal to XC. This is called resonance. The expression of resonating frequency is given by omega R is equal to 1 by root over LC, where L is the inductance of the circuit and C is the capacitance present in the circuit. Thank you.